Hello everyone, I am Manish from EC department. Today I will be discussing about Labsheet-6, which is given by our VP Singh sir. So basically, in filters can be designed in analog domain or in digital domain. In digital domain, we have two types of filters. One is IIR filters and other one is FIR filters. Because filters are well studied in the analog domain, to design any filter, first we will do the corresponding design in the analog domain, and then we will convert into the digital using impulse invariance method or bilinear transformation method. IR filters are recursive in nature and FIR filters are non-recursive in nature. Before going further, I will explain four main filters in detail. First one is low pass filter. We have pass band frequency and stop band frequency. Less than pass band frequency, it will pass the signal, and after stop band frequency, it will strongly attenuate it. Similarly, in the high pass, before stop band, it will highly attenuate, and in the pass band, it will pass the given signal with less attenuation, or the gain will be around zero, like it is not amplified or it is not attenuated. Similarly, in the pass band, uh, we will pass a range of frequencies between pass band 1 and pass band 2. Similarly, in band stop, we'll stop a range of frequencies between stop band 1 and stop band 2. In the pass band, sometimes the minimum attenuation may be different in the two stop bands. Let us say if it is A1 in stop band 1 and A2 in stop band 2, then in order to design this band pass filter, we need to consider the attenuation which is maximum in A1 and A2. Let us say A1 is greater than A2, and A1 is the minimum attenuation required in the stop band 1 and A2 is the minimum attenuation required in the stop band 2. If you design a filter considering the A1 as attenuation, minimum attenuation, then automatically the designed filter will attenuate more than A2. Similarly, in the band stop filter, sometimes here we may have peak ripple pass band 1 and peak ripple pass band 2. Even in this case, you should consider the worst case scenario, that is you should consider the maximum RP value. So these ripples are nothing but the maximum amplitude variation which can be tolerated in the pass band. So if you consider if you construct the filter using this maximum ripple factor, so minimum ripple factor will be automatically included in this. So you should be careful in taking attenuation constants and peak pass band ripple in the band stop filter and band pass filter. Till lab 5 we have learned how to design the filters in analog domain. Now to convert from analog to digital, we have two methods. One is impulse invariance and bilinear transformation. In impulse invariance, after getting the filter function in the analog domain as the partial fractions, we will do sampling. First we will do inverse Laplace transform, and then we will get this expression, and then we will do sampling and convert it into the digital domain. After getting into the digital domain, we will do the Z transformation. So basically, the idea of impulse invariance method is to map the poles in the S domain to the Z domain by using Z equal to e power st. So if you if you substitute Z equal to R into e power j omega and e power st as in place of S, if you substitute sigma plus j omega, and to get R equal to e power sigma t, we have W equal to omega t. So this is the required condition in the impulse invariance method. In the MATLAB, first we will get the residues by using this inbuilt function, and then we will map the poles in the S plane to Z plane, and then we will scale the residues, and then after getting the residues in the Z plane, again we will convert them into a normal form. That's the reason we are using residue here. It converts residues and poles into a normal polynomial form, like s square plus sorry, z z inverse plus 1 by 2 into z power minus 2 plus 2. So the residues command will convert the poles and residues into polynomial form. So after converting from the residues and poles to the polynomial form, we will take bc equal to real part of bc and az equal to real part of az. If you see in the derivation part, if we take w equal to omega t, it is getting cancelled. The imaginary part is getting cancelled here. bc and az can have some imaginary values due to some mathematical errors and computations. They will be very less. Now the other method to convert from analog to digital is by using bilinear transformation. In the impulse invariance method, we are mapping the poles in the S plane to Z plane, but the high frequencies will be also mapped to the same place in the Z domain. So that's the drawback of the invariance. So to avoid that, we are using bilinear transformation. If you do this transformation, then every pole in the S plane will be uniquely mapped to the Z plane. In bilinear transformation, even we are getting a unique mapping from S plane to the Z plane. The higher frequencies are getting compressed in the Z plane, and the lower frequencies are getting expanded. So to address this issue, we are using pre-warping. Like suppose if there is a 1000 Hz cutoff, if you apply the bilinear transformation, then in the Z domain, the cutoff frequency is changing to 900 Hz. So instead, we will be using some other value in the S plane so that it will give the 1000 Hz in the Z plane. So this is what pre-warping means. So now to pre-warp the values, the corresponding formula is omega equal to 2 by t into tan of w by 2. We can get this formula from from the transformation formula itself. S equal to 2 by t into 1 minus z inverse by 1 plus z inverse. If you substitute z equal to r into e power j omega and r equal to 1, then you will easily get this relation. And this is used to pre-warp the frequencies. Now we will discuss how to design a low pass filter using bilinear transformation. So we will having the information in the digital domain, like this is the requirement of our filter. So we are using bilinear transformation. The poles will get uniquely mapped in the Z plane, but the higher frequencies are getting compressed and lower frequencies are getting expanded. So to address that issue, first we will pre-warp the frequencies, and we will get the new frequencies omega p and omega s. Now we will design the analog low pass filter by using this new omega p and omega s. And we know we can design this analog low pass filter by using Butterworth Chebyshev or Chebyshev 1, Chebyshev 2 or elliptic. And after designing the analog low pass filter, we will just use bilinear transformation to transform from S plane to the Z plane. We can also convert low pass filter from analog to digital by using impulse invariance method. In this method, the relation between omega p and wp is given as this. So by using the new omega p and omega s values, we will design the filter in the analog domain. Similarly, we did in Labsheet 5. So after designing this, we will get the h of s transfer function, and now we will convert this into digital domain by using the impulse invariance method. And for to transform into impulse invariance method, we have seen how to convert from analog to impulse invariance method using the MATLAB approach or a theoretical approach. Now let us see an example on how to design a digital low pass filter using Butterworth, and we have the specifications given in the digital domain. We have 0.2 pi as passband, 0.3 pi as our stop band, and 1 dB peak passband and 15 dB. So we will design this filter using both impulse invariance and bilinear transformation. We will see how to do this. So here I have written the MATLAB code for designing this low pass filter. First we will be using bilinear transformation. So as we are using bilinear transformation, first we need to pre-warp the frequencies, and here I have done it. And we will calculate the analog transfer function by using these two lines. And after getting the analog transfer function, we will be converting it into digital by using this bilinear. And this bilinear is inbuilt function. And after transforming into the Z domain, now we will get the frequency response of the corresponding filter. And here I have plotted the gain of the filter. So here you can see the passband is around 0.2 pi. Here I have taken the normalized units. So here I have 0.2 in the x-axis. So the passband is 0.2. You can see at the passband till passband the gain is near to 0, and after stop band our required condition was at the stop band we need a minimum attenuation of 15 dB, and here we are getting it. At stop band you can see there is a attenuation of 15 dB, and after the stop band you can see the attenuation is increasing so on. So our required condition was minimum it should be 15 dB, and here it is satisfied. So by this you can check, you can verify your filter response also whether it is correct or wrong by observing the plot. And coming to the uh, phase response, here I have plotted both in the normalized units. Here you can see the phase is clearly non-linear. So that's the drawback of this IR filters. In IR filters we will get a non-linear phase. So now here I have designed the same low pass filter by using impulse invariance method. So in the impulse invariance method, there is no need of pre-warping. If we take Ts equal to 1, directly we can substitute the omega Wp and Ws values as omega p and omega s. The conditions Rp equal to 1 and minimum stop band attenuation is 15 dB. Now in these lines we have calculated the order and cutoff frequency and the transfer function of the filter in the analog domain. Here I have defined a separate function for to convert from analog from analog to digital using impulse invariance method. I have implemented the same code which I explained in the PowerPoint presentation. So this function basically takes uh, the coefficients of numerator and denominator in the analog domain and the TS value, and it returns the numerator and denominator in the digital domain. So here now the NZ and DZ will store the values of Z domain. After getting the numerator coefficients and the denominator coefficients in the Z domain, now we will be using the frequency plot to plot its frequency response. So I have plotted the gain. So you have got this graph now. So how to check whether it is correct or wrong? We will check with the given uh, given requirement. So till passband 0.2 the attenuation is about 0, and at stop band we are seeing a attenuation of 15, which is exactly at this point. And in between pass band and stop band, we have this gradual roll off. So this is due to transition band. So that's the reason a pass band and stop band is never equal in the uh, practical case. So after stop band, you can see the frequencies are attenuated more than 15 dB. So like this, you can check whether your answer is correct or wrong after implementing the code. If you see the phase response plot of the impulse invariance method, you will see the phase is similar to that of the bilinear transformation method. In both cases, the phase is non-linear. So that's the main drawback in the IR filters actually. Yeah, so far we have discussed how to design low pass filter using IIR and bilinear transformation. Now, to design high pass and band stop, we cannot directly design these filters. So what we will be doing is, we will design a low pass filter and then we will transform this low pass filter such that it will give you the uh, high pass filter, band stop filter. So we will design the analog low pass filter prototype and then we will transform it in the S domain. So actually we can do this transformation in the S domain, or else after converting into the digital frequency, after getting into the digital domain, we can also transform corresponding high pass filter after getting the digital frequency. In this video, I will be covering on how to do the transformation in the S domain and then we will convert it into the digital domain. So basically what we will do is, we have the requirements of high pass filter, say omega p, omega s and so on. What we will do is, we will construct a corresponding low pass filter and then we will transform it in the S plane and then we will do the bilinear transformation or impulse invariance transformation to get the high pass filter in the digital domain. Now we will look in detail how to convert these things. Let's discuss how to design a high pass filter using bilinear transformation. So we will be having the specifications in the digital domain. Let's say WCAPS, WCAP, RPAS. First, what we will be doing is, if we are using bilinear transformation, first we will pre-warp the frequencies. Step 1. And then now we have got the omega cap P, omega cap S. Now we should design a corresponding low pass filter and then we will apply bilinear transformation for it. So to get the low pass filter specifications, as the specifications of this and low pass filter will be not same. So basically what we are doing is, we will be calculating a corresponding low pass specifications and then we will be transforming it to get the high pass specifications. So step 2 is calculate omega p and omega s. So these are to design the low pass filter, not high pass filter. So after getting these values, substitute here to get omega p and omega s. Here we are taking omega p equal to 1 because basically we'll design the low pass filter taking omega p equal to 1 and later in transformation we'll be using the corresponding omega p cap so that it will match our actual requirement. So till now we have designed we have got the specifications of low pass filter omega s and omega p. Now we should design this low pass filter by using Butterworth or Chebyshev or elliptic. And after getting the low pass filter specifications, now we will use the inbuilt MATLAB command to convert low pass to high pass. So whatever the numerator and denominator you get in the low pass, you just plug them in this command, and we are giving a extra omega p cap because initially we have designed the low pass filter by taking omega p equal to 1, but our requirement is omega cap p. So that's the reason now we will scale for omega p cap. So that's the reason we are implementing here. So what this LP to HP internally does is it uses this transformation to transform from S domain to P domain. Now after getting this, after this command, we will get the we will get a transfer function of high pass filter. Now the design of high pass filter is done in the analog domain, but still we want the design in the digital domain. So that's the reason we will do bilinear transformation at the end to get the uh, digital transfer function. Now let's look at the example to design a digital high pass filter using Butterworth. Pass band is this, stop band is this, RP is this, AS is this. Here let's design this using only bilinear transformation, and we will also verify whether it is correct or wrong. So here I have written the MATLAB code for the high pass filter. So as we are using bilinear transformation, we need to pre-work the frequencies first, and then to calculate the low pass filter specifications, I have taken omega p equal to 1 and omega s equal to omega p into omega p cap divided by omega s cap. And after getting the low pass specifications, it's just calculating the order omega c and the transfer function of the low pass filter in the analog domain. Till here we have got the low pass filter in the analog domain. Now we will be using this low pass to high pass command to convert from low pass analog to high pass analog. Here we are giving omega cap p because we have constructed the low pass filter taking omega p equal to 1. So we need to scale it back to the actual requirement. So that's the reason we will be using omega p cap in the LP to HP command. So what this command is, what this command gives is it gives the transfer function of high pass filter in the analog domain. Now we will be using the bilinear transformation to map the each and every poles in the analog domain to the digital domain. And after getting the numerator and denominator in the digital domain, now we will be using the frequency plot to plot its response. So here you can see I have plotted the filter response of the high pass filter. The x-axis is in the normalized pi units, so it is 0.1 pi, 0.2 pi, 0.3 pi and so on. So what high pass filter does is till stop band it will highly attenuate the signal, and after the pass band it will pass the signal with no attenuation. So that is what happening here. Here you can see at the stop band edge, which is 0.5 pi, you can see the attenuation is exactly 74 dB. So here you can check this point at the stop band frequency the attenuation is minus 74 dB. Similarly, in the pass band, if you zoom it, you can see there is no much change in the gain. The gain is 0. It means how much ever the input amplitude is there, that much is passing through the pass band. That much amplitude is coming to the output. That is no amplitude is changing. And in between we are seeing this curve due to the transition band. So like this you can verify whether you have got the correct uh, frequency response in the digital domain of the high pass filter or not. Now here I have plotted the phase response of the high pass filter. See, what we can observe here is the phase plot is not linear. Here I have plotted the both x-axis and y-axis in the normalized units, that is in terms of pi. So here the observation is, here we can see the phase is clearly non-linear. Now we will see how to design a band pass filter using bilinear transformation. So the step 1 will be same. First we need to pre-warp the frequencies, and then in the step 2 we need to verify whether this condition is satisfying or not. If these are satisfying, then we will calculate the bandwidth. The bandwidth in the band pass filter is omega p2 minus omega cap p2 minus omega cap p1, and we will calculate the omega naught cap. This will be our step 2. So step 1 will be pre-warping the frequencies, and step 2 will be calculating this thing. So what we will be doing is we will design a low pass filter, and then we will transform this low pass filter into band pass filter in the analog domain, and then we will convert it into the digital domain. Here the specifications of low pass filter are not same as the specifications of the band pass filter. So what we will be doing is, in step 3 we need to calculate the specifications for the low pass filter, such that whenever we transform that in the analog domain, the filter should have the specifications of the band pass filter according to our required specifications. So what we will be doing is, first we will fix omega p equal to 1 in the band pass filter, and we will calculate omega s value using this formula. We have substituted omega cap s1, and we have got, let us say it is omega s1. So similarly, if you substitute omega cap s2 in place of omega cap s1, you will get two values of omega s, which are omega s1 and omega s2. So which value we need to take to design the low pass filter, and we need to take the minimum value out of these two values, and I will explain this in detail in the MATLAB why we are taking the minimum value instead of uh, the maximum value. So after getting the minimum value of omega s, now we will design the analog low pass filter in the S domain, and we will transform it using the inbuilt MATLAB command to the band pass filter. So after getting the filter response in the analog domain, we will be using bilinear transformation to get in the digital domain. Here we are designing a low pass filter, but we had specifications in terms of band pass filter. So what we will be doing is, we will fix omega p equal to 1, and we need to find omega s. Let us say this is omega s1, and if you keep omega s2 in place of omega s1 cap, you will get another value of omega s, which is omega s2, which is nothing but omega p into omega naught square minus omega s2 cap square divided by omega s2 cap into bandwidth. Construct a low pass filter, we only have to give four specifications: omega s, omega p, rp, and as. So in omega s1 and in omega s2, we will take minimum of omega s1 and omega s2, because see, if we have if we consider omega s1 is greater than omega s2, so what this bandpass filter is will be doing is, it will pass the frequencies which are present in the pass band, and it will stop the frequencies which are in the stop band. So we are having two omega s values, omega s1 and omega s2. Suppose if you consider omega s2 and design the corresponding low pass filter, then what you will be seeing is, you will be seeing the minimum attenuation as will be satisfied by the omega s2, but at omega s1 the minimum attenuation may not be satisfied. So in place of taking omega s2 to design the low pass filter, if you take omega s1 and design the low pass filter, at stop band 1 itself we are meeting the required minimum attenuation. So after it crosses s2, the attenuation will be more than the minimum value, which is okay. So that's the reason we are taking the minimum value of omega s1 and omega s2. Now let's design a digital bandpass filter using the Butterworth approximation. We are given pass band frequencies, stop band frequencies, peak band, and minimum stop band attenuation. So here I have written the code for bandpass filter. So first we will be pre-warping the given frequencies, and then we will be calculating the corresponding omega cap naught, and we will be fixing the omega p equal to 1 for the pass band to design the low pass filter. So here this code is for calculating the bandwidth. Here I have written the two equations for calculating omega s1 and omega s2, and I am taking omega s as the minimum value of omega s1 and omega s2, and after getting the minimum value, I have designed the low pass filter, and then by using the inbuilt MATLAB command, I have converted the low pass to band pass filter, and then I have done bilinear transformation, and then I have plotted the frequency response. Now I have got this frequency response in the digital domain. Now how to check whether this response is correct or wrong? According to our specifications, this is a bandpass filter. According to our specifications, it should pass the frequencies which are present in between 0.45 and 0.65. And if you see here, the frequencies which are present in between 0.45 and 0.65, they are getting passed with gain 0. Means how much the input is there, that much input is coming. It is not attenuated or it is not amplified. And if you see at the stop band, we required a minimum attenuation of 40 dB. Here at the stop band edge 1, you can see the attenuation is more than 40 dB, which is still fine, because if we are getting more attenuation than the required, it is good, right? That's what our intention is. minimum attenuation is 40, and in the stop band edge 2 we are getting the minimum attenuation for minus 40 dB, which is exactly the required amount. Suppose instead of taking omega s as a minimum of two values, if I take maximum of two values and if I run the code, you can see here at omega s1 the attenuation is minus 40 dB, which is satisfying the required condition. But at the stop band edge 2 you can find that it is not satisfying the required minimum attenuation. So that's the reason we are taking the minimum value for omega s. Here you can see the attenuation at edge 2 is around minus 30 dB. So here only edge 1 is satisfying. To make the both edges satisfy simultaneously, we are taking the minimum value and we will design the filter. So here you can see at edge 1 the required attenuation is 40 dB, but I am getting around more than 40 dB, which is still fine, which is good. And at the stop band edge 2 I am getting minus 40 dB, which is exactly the required specification. Like this you can verify whether your filter response is correct or wrong. And I have plotted the frequency phase plot of the bandpass filter. In the x-axis and y-axis are both are in the normalized units. Here the observation which you can get is the phase is clearly non-linear. Now we will discuss how to design a bandstop filter using bilinear transformation of given specifications. So our step 1 will be pre-warping, and the step 2 similarly in the bandpass filter we have checked the conditions. So if these conditions are given in question, they will be automatically satisfied. But in some cases when we need to decide the passband 1 and passband 2, in that case these conditions will help us to take the close value of passband 1 and passband 2. So we will be calculating the bandwidth. Here the bandwidth is omega cap s2 minus omega cap s1, and the omega naught cap is same. And step 3 will be to design the low pass filter. And in the designing the low pass filter we require omega p and omega s. To design bandstop filter we will fix omega s equal to 1 and we will calculate omega p. Similar to the last bandpass filter, now to get the specifications for the low pass filter, we fix omega s equal to 1 and we calculate omega p. We get omega p, we get two omega p values, that is omega p1 corresponding to omega cap p1, and we get omega p2 which corresponds to omega cap p2. So similarly we have taken a minimum value of omega s in the previous question. So here we will be taking the minimum value of omega p1 and omega p2, and we will take this as omega p, which will be used to design the corresponding low pass filter. So I will explain why we are taking a minimum of these two in detail in the MATLAB. So till now we have designed the low pass filter. So we have got omega s and omega p. Now we need to design the analog low pass filter by we will use a Butterworth, Chebyshev or elliptic depending on the question. And now we need to transform the analog low pass filter into the analog bandstop filter. So in MATLAB, we'll be having a inbuilt command which will do this work for us. If you want to do theoretically, then this is a transformation which you need to apply. After applying the inbuilt MATLAB command, converting from low pass to band pass, we'll be getting the coefficients of numerator and denominator in the analog domain. So we'll be using bilinear transformation to convert from analog to digital here. So this will be the required step. It is similar to band stop only. The only change here is the transformation function is different and the bandwidth is different, and calculation of omega p is different. There we have fixed omega p equal to 1, and here we are fixing omega s equal to 1. Now let's design a bandstop filter using Butterworth approximation. We are given pass band, stop band, minimum attenuation. So here I have designed the bandstop filter. First, I have pre-warped the frequencies, and then I have calculated omega naught cap, and I have calculated bandwidth. Now I calculated omega p1 corresponding to omega cap p1, and omega p2 corresponding to omega cap p2, and I have fixed omega s equal to 1. And to design the low pass filter, we said we will take minimum value of omega p1 and omega p2, and after getting omega p and omega s, we will get the order and the transfer function in the analog domain. Here we are using the inbuilt command to convert low pass into band stop. After converting from low pass to band stop, now we will convert using bilinear transformation into Z domain. And using this frequency command, I have plotted the frequency response transfer function response of the filter. So the plot for bandstop filter is as following. What bandstop filter does is it stops the band of frequencies which are in between the stop band edge 1 and stop band edge 2. Here you can see at stop band edge 0.45 and 0.65, the required minimum attenuation was 40 dB, which is meeting the conditions at the two edges simultaneously, and in between the attenuation is more than 40, which is a general characteristic of the bandstop filter. And till passband edge 1, the gain is almost 0, and even after the passband edge 2, the gain is almost 0. It means the signal is not getting amplified or not getting attenuated except in the stop band edges. And in between here the gain is changing. It is due to the transition band. As the practical filters will have transition band, this thing we are seeing due to the transition band. So what if we take maximum value of this omega p1 and plot the response? See, here at the stop band edge 1 and stop band edge 2, we expected a minimum attenuation of 40 dB, but we are not getting minimum attenuation of 40 dB. Here the gain is around almost 0. So you have omega p1 and omega p2, and it is a band stop filter. So if we construct a low pass filter such that it allows the frequencies which are below pass band, and it will start attenuating after the pass band 1, and if we take omega p2, it will pass these frequencies and it will start attenuating these frequencies in the low pass filter. So we got correct answer when we have taken omega p1, because below this the frequencies are allowed and above this these are strongly attenuated. In case of omega p2, if we see in the attenuation, above omega p2 it is getting attenuated, which is fine, but below p2 the signals are not getting attenuated. They are not getting attenuated. So that's the reason when we have taken omega p2, we have seen the signals are not as attenuated as we expected. But whereas when we have taken omega p1 and designed the filter, the signals are attenuated as the required specifications, because omega p1 attenuates this all and omega p2 attenuates these all frequencies. When we take omega p2, these frequencies are not attenuated. So that's the reason we did not get a correct frequency response when we used omega p2. So that's the reason we are taking the minimum of omega p. I know I may have said some mistakes. Feel free to correct me and comment the mistakes, and if you have any suggestions you can comment it. And thank you. If you find this video useful, feel free to share this with your friends. Happy learning. Bye.